of electromagnetic radiation. And so what we're looking at is the situation where we are near resonance with some transition in our atom being driven by quasi-monochromatic light. So we can think about this as a plane wave, although it's not important that's a plane wave. It could be a standing wave, just the fact that we have some fairly well-defined frequency. And if we are in the electric dipole approximation, then our interaction Hamiltonian is the interaction of the electric field associated with the electromagnetic wave and the electric dipole operator of the atom. And if we express our general plane wave in terms of the real part of this complex amplitude with a polarization vector and a propagating wave, then our interaction Hamiltonian breaks up into two terms we generally call the positive and negative frequency components. And when you go through the usual derivation based on time-dependent perturbation theory, then you get from Fermi's golden rule the transition rate between some initial state and some final state, which depends on the matrix element of either the positive or negative frequency component, depending upon whether the initial and final state are greater, if the final state is greater in energy by h bar omega, or less than in energy by h bar omega, corresponding to absorption or emission. And this expression only really makes sense when we are integrating over some spectral distribution of either the density of states and or some density of modes, so that we don't really have purely monochromatic radiation. For example, we have quasi-monochromatic radiation with some spectral density of the power at a given frequency. And from this we saw last time, we looked at the absorption rate in the kind, if we had, for example, absorption of black body radiation, specified by a energy density per unit frequency interval, then the absorption rate was written as something we typically call the Einstein B coefficient times the spectral energy density. And B here was equal to 4 pi over 3 the square of the dipole matrix element between the ground state and the excited state, h bar squared. That's the Einstein B coefficient, I believe. Right? I think that's right. Okay. And then we also talked about spontaneous emission. Well, and of course, this would also be equal to the rate of absorption from the ground state to the excited state is given by this. That's what we call, that's our absorption rate. But in addition, if we had started in the excited state, then we would induce transitions to the ground state by the same rate. And this is what we call stimulated emission. It's exactly the same rate. However, in addition, we saw that there is spontaneous emission, in which we interpreted as be thought of as stimulated emission by the vacuum. And so the spontaneous emission rate is the B coefficient times the vacuum energy density, which we call the Einstein A coefficient, which is also the natural line width of the excited state. And the Einstein A coefficient, or the spontaneous emission rate, is 1 over the lifetime, is equal to 4/3 the dipole matrix element squared times omega cubed. Okay? So in addition to the stimulated emission, there is also spontaneous emission at the rate gamma, given by, which means that there is, even in the absence of any electromagnetic radiation, the excited states are generally not stable. They're not true eigenstates of the total system because of the interaction with the vacuum fluctuations. All right? Okay. So, well, this is a particular picture that we have of absorption emission, in which we think about rate processes, in which we think about there are energy levels of my atom or molecule or what have you, and the effect of the perturbation by the magnetic field is to cause population to jump between those different levels. But that's a little bit narrower of a view, because of course we know that indeed, according to quantum mechanics, evolution is generated by a unitary time evolution operator, in which probability amplitude continuously evolves according to the time-dependent Schrödinger equation. So really what we want to talk about today is life beyond Fermi's golden rule. You know, in many subdisciplines of physics, as a biased quantum optician here, you know, you talk to your typical condensed matter physicist and it's all about correlation functions and what's the ground state. It's all statics. Dynamics is, you know, you just throw in Fermi's golden rule and it just tells you how things, how you absorb and emit your matter if you're not in equilibrium. And that's a very useful picture to have when we're talking about incoherent processes. And we're going to talk a little bit about the difference between coherence and incoherence in the next few lectures. But the point here is that these two particular examples are examples of incoherent processes. I'm talking about not a well-defined electromagnetic oscillator that's oscillating with a well-defined frequency, really. What I'm talking about is chaotic light that's coming from this light bulb or from a thermal source like the sun. If I were to look at the electric field as a function of time, it is not oscillating with a well-defined frequency, but in fact is jumping all over the place because there's a very chaotic process by which all the collisions of the electrons being driven in this gas of neon tubes or in the sun, which causes the emission, the radiation to be constantly interrupted. All the oscillations are not with well-defined phases. Moreover, when we're talking about spontaneous emission, we're talking about vacuum fluctuations, which are also highly incoherent. So Fermi's golden rule, if you go back, I don't know if you remember or if you've done this in your quantum mechanics course, the derivation of Fermi's golden rule, you feel like you have to stand on your one foot and, you know, be grasshopper and make sure you don't move. And you're talking about perturbations, which are supposed to be short-time evolution, but then you take the limit as t goes to infinity, and you say this thing is really for the long-time limit, but that's okay because really, I don't know why. Well, it's all buried in the fact that the situation for which Fermi's golden rule holds are the situations for which we have this distribution, this density, this spectral density of final states or spectral density of driven modes. But that's not all there is in the world. For example, if I'm thinking about say I have an atomic clock in cesium. Okay, here's my 6-1. That's 1/2 ground state. Here's my n = 0. And I put on a microwave radiation, electromagnetic wave, which is driving this transition. If I somehow started my atoms here, I can calculate, if I like, I can use Fermi's golden rule to try to calculate the rate of absorption. In this case, it will be a magnetic dipole transition as opposed to an electric dipole, but that's no big deal. You just put in the magnetic dipole moment rather than the electric dipole moment. But the microwave oscillator here is not black body radiation. It's, you know, quartz oscillator, I mean, RF or microwaves, those are very well-defined frequencies. And moreover, there's no density of states here. There's 2 levels. I mean, maybe, you know, the lifetime of this is so darn long, I don't even know what it is. I don't know how long it is compared to the age of the universe, but it's forever. For all intents and purposes, there's 1 level up there. There's no spontaneous decay here. Why? Well, for 2 reasons. You remember that this depends on the square of the matrix element. Well, now we're talking magnetic dipoles rather than electric dipoles, so that's down by 2 factors of the fine structure constant. And moreover, we're talking 9.2 gigahertz. That's a low frequency compared to, say, an optical transition, and that's cubed. So there's no spontaneous emission to worry about. So Fermi's golden rule just doesn't work. context.
That's what you wrote for the stage G, 5.5, or on the left?
This is the 6s1/2
Okay.
ground electronic manifold of cesium. And this is my ground state, and this is my excited state, for example. Moreover, we have nowadays, and nowadays has been a long time now, although quantum mechanics textbooks haven't been modified probably sufficiently in the last 60 years, maybe 50, we have lasers. We're not just talking about absorption and emission of lamps. We're talking about absorption and emission of light that's generated by lasers. And lasers, of course, are extremely narrow in their spectral distribution. They, too, have well-defined spectral energy density. So, for example, I might have the situation, let's think about, suppose I have in some atom, let's say I have in helium, suppose I have the singlet as 0 ground state, this is cesium. Well, here I'm going to take a different example because it's one that's actually used. Here's a calcium plus ion, something that's used in ion-trapped quantum computing. And the ground state here is some S state. I don't remember what the principal quantum number is. And then up here, there's some D state. I don't know what it is in calcium. Maybe it's 4. Calcium, 4S and 4D? I think so. So this is, of course, a quadrupole transition. But I could drive it if I'm near resonance, except it has an extremely long lifetime. And so over the course, again, like the case of my atomic clock, this state is so long-lived that for all intents and purposes, at least for some time considering whatever the lifetime of that is, probably seconds. So if I do an experiment in a millisecond, I can ignore the spontaneous emission. And again, these are just 2 levels separated by some laser frequency. So again, if I wanted to look at the dynamics of this atom coupled to this electromagnetic radiation, this picture of quantum jumps between levels is not the right picture. What we have is more coherent evolution that's described by the time-dependent Schrödinger equation, which we shouldn't forget. So, what I want to talk about then is this problem, the problem where I have 2 discrete levels of my atom. They could be the absolute ground state, doesn't matter, but there are 2 levels. One's lower, I'll call it the ground state. One's higher, I'll call it the excited state. And we have, well, here it is. We're driving this with some frequency. And we want to look at the time evolution of the wave function or state vector of the atom driven by this single frequency. Okay? Well, how do we do that? Well, we go back. Unfortunately, I erased it. It was a bad move on my part. But all we want to do in this case is solve the time-dependent Schrödinger equation. So we want to solve the standard equation. Okay. Generally, it's a hard thing to do. You remember when the Hamiltonian does not commute with itself at different times, you can't just exponentiate the Hamiltonian. You have to worry about Dyson series and time-ordered products and all of that, and that's where we get into the business with time-dependent perturbation theory. But in this particular case, for this very limited circumstance where we have two levels connected near resonance with some driven field, then to good approximation we can solve this exactly. And that's the problem of Rabi oscillations that we're going to talk about today. So, what are we doing here? Well, so my Hamiltonian here involves two pieces. There's the atom. There's the Hamiltonian describing everything we've done in the first weeks of the semester. All the atomic structure is here. And then we have the interaction Hamiltonian, which is time-dependent because we're applying a time-dependent force and we're treating that force classically. So we're treating the field classically here. Now, when we have this circumstance where we're near resonance, between two levels that are going to be called G and E, there could be, these two levels in the calcium atom or these two levels in the cesium atom, what have you. Then we know from our studies of time-dependent perturbation theory and beyond that we can restrict our attention, this complicated thing that we've spent weeks and weeks doing, Hartree-Fock and closed shell mean field theory and whatnot, is just reduced. There's just some structure, whatever it is. And moreover, because we're near resonance, we can restrict our attention to a two-dimensional Hilbert space. So although the atom is described by an infinite dimensional Hilbert space, it's got the continuum, it's got all kinds of states in it, there's only two orthogonal vectors in the Hilbert space where all the probability amplitude lies to a good approximation, to an excellent approximation for all times. In which case, our problem reduces to solving the Schrödinger equation for a 2x2 matrix, where one of the states we call G, for example, this one, and one of the states we call E. It's that one. Okay. So our interaction Hamiltonian, let's write it down again. Let's imagine, although it's not the case for this particular, let's look at a different case where, because we're going to ultimately add in spontaneous emission. Let me imagine this to be a dipole allowed transition. Well, that will mean that this description will only be good for times short compared to the spontaneous emission time. But let me just focus on that for the moment. So my interaction Hamiltonian, we wrote it down just a moment ago. this Hamiltonian now is restricted to this two-dimensional subspace. Okay? Which means we can, this Hamiltonian can be restricted to a projector projecting on this two-dimensional subspace, where my two-dimensional projector is project onto ground and project onto its side. Okay? Now, the dipole matrix element, the dipole operator only has off-diagonal matrix elements, right, because of parity. So these eigenstates are eigenstates of parity, so there is no expectation value of the dipole operator. There are only off-diagonal elements of the dipole operator. Okay, so so now if I write this out, I have the dipole matrix element let me be a little more careful here because so I'm just doing this projection on this first term here. Times E0 e to the plus Hermitian conjugate. Okay? So that's just doing that projection onto that subspace where the diagonal matrix elements are 0. Now, we can always choose the phases of these wave functions so that these are real. For some particular choice of the phase of those wave functions which are irrelevant. And that's the standard procedure. In which case, we can write this in the following way. Minus 1/2 of an energy that I'm going to call h bar capital omega. We have some phase, which generally depends on the position, e to the minus r eg plus g e plus Hermitian conjugate. Where h bar omega is the energy associated with the interaction. That is to say, it's the dipole matrix element times the amplitude of the electric field. D times E is an energy. D dot E is an energy. So this is the energy associated with that interaction. And the frequency, if I divide that energy by h bar, is known as the Rabi frequency for reasons that will become clear in a moment. Okay? The phase here is equal to the local phase at the position of the atom, and then whatever the phase of the laser is. So the phase as a function of R is, I mean, this thing could have a phase. It doesn't have to be it could be a complex thing. Is the propagation phase plus the phase of the laser. Okay. So my interaction Hamiltonian can be written now as cosine omega t minus phi of r times GE plus EG. All right? Moreover, it's chalk here. Our atom is also projected onto this two-dimensional subspace. The two states were eigenstates of the atom alone. We have the ground state energy plus the excited state energy. Okay? Now, it really doesn't matter where we take the zero of energy. The zero of energy can be taken wherever we like. We have the situation where we have two levels. We have the ground, we have the excited, we have our, let me call this, just to be clear, let me imagine this to be a laser, so I'll call this the laser wave vector and the laser frequency. So we are situation where we're near resonance. There, in this circumstance, where we call the zero of energy, well, in any circumstance where we call the zero of energy is irrelevant. It's just a question, it's the relative energies that define dynamics. And there's a couple of different choices when you're dealing with a two-level atom. Sometimes you'll see we'll choose the zero of energy halfway between the ground state and the excited state. Or sometimes we'll take the ground state to be zero energy. So that's the convention I'm going to take today. I'm going to call the ground state energy zero, and then the excited state energy is equal to the energy associated with this frequency difference, the Bohr frequency associated with the difference in energy times h bar. Okay? So I'll just write this as h bar omega Eg times Ep.
What's the difference between omega Eg and omega L?
Omega L is the frequency of the laser. Omega Eg is the resonance frequency of the atom. That is to say, omega Eg is the energy of the excited state minus the energy of the ground state in units of h bar. So this is a property of the atom, and this is the applied force.
We assume that there is
This is not necessarily exactly on resonance.
Okay.
Okay, so the difference we define when we're not exactly tuned to resonance, we say we are detuned away from resonance. So what we call the detuning is delta is the applied frequency minus the resonance frequency. And so if delta is less than 0, we call this red detuning because the frequency of the applied light is slightly redder than the resonance frequency. And when delta is positive, we call this blue detuning because the applied frequency is slightly bluer than the resonance frequency. So now we can now we have our Schrödinger equation. We can write down the differential equation. So our state as a function of time is projected onto this two-dimensional subspace and thus has two probability amplitudes. Some probability amplitude to be in the ground state and some probability amplitude to be in the excited state. And my Hamiltonian can be expressed as a 2 by 2 matrix in this basis. It has diagonal matrix elements, which, if I order my basis this way, are the energies associated with the excited and ground state. I'm taking the ground state energy to be 0, excited to be this, and I should make the matrix bigger because it won't fit my stuff, so sorry, make your matrix bigger. We have minus h bar omega over 2 cosine.
Doesn't that 2 get sucked in when you make the cosine?
It does, thanks. Yeah, it does. 2 gets sucked in when you make the cosine. I agree.
Sorry for phrasing it straight.
It's exactly right. 2 gets sucked in. Yeah. I'm going to choose the phase to be 0. We'll come back to that in a moment. Let's just focus on this special case. Okay, so this is my Hamiltonian matrix in this 2-level atom. So now we can solve the Schrödinger equation. We have d by dt of the state vector is minus I over h bar. And I'll put that in here, 0 minus omega cosine omega dt minus omega cosine omega t omega eg. E. Okay, so writing that out, d by dt of the ground state amplitude that is coupled to the excited state amplitude and the excited state coupled to itself according to the eigenfrequency, and then coupled to the ground state through Rabi frequency. Well, that's pretty nice. It's just 2 coupled ODEs. But unfortunately, there is no solution, exact solution to this equation. This is a set of ordinary differential equations, but with time-dependent coefficients. Generally, you can't solve them. Generally, those are chaotic, right? I mean, you know that from theory of dynamics. You can't generally solve such equations. They're not integral in general. However, we can solve them to an excellent approximation when we're near resonance, which is to say delta, the magnitude of delta, is much, much smaller than the resonance frequency or the applied frequency. And also, omega is much, much less than this, the Rabi frequency. So this is the, especially for near resonance, weak driving. Now, what weak means is this, but as we'll see in a moment, it's not really that weak in any sense because there's resonance, right? I mean, if I push on the Tacoma Bridge at its frequency with very weak wind, it's going to blow apart. So we will get a very big effect for a weak field. What does this mean really? What this really means is that remember what this is. This was D dot E, basically. Whereas at this frequency here, well, that's something like, it's something on the order of the Hartree, some fraction thereof, some few electron volts, right? So what we're really talking about here is a situation where the electric field is weak compared to the internal electric fields inside the atom. I mean, now if we start getting that, I mean, for example, the whole two-level approximation is a horrible one. This is not a weak perturbation. But even before we get to those extreme fields, if we started to get the Rabi frequency on the order of the oscillation for the resonant frequency, well then this is just a bad approximation. Okay, and what does that mean in the context of optical? Well, the frequency that we're talking about optical frequencies, we're talking about 10 to the 15 hertz, 1,000 terahertz, whereas typical Rabi frequencies associated with CW laser beams and dipole allowed transitions with high oscillator strings, megahertz, some megahertz. So this is an excellent approximation.
What happens when you start going that fast?
Well, there's a few things. I mean, if I start, to the degree to which the two-level approximation is still good, which might not be because there's off, as we'll see, the degree to which I drive to other states depends on the detuning. But to the degree to which I start getting on that order, what we'll see is a moment, there are corrections to the rotating wave approximation. So we're about to talk about the rotating wave approximation. And you get shifts in the frequency they're called the Bloch-Seeger shifts. Let's talk about that more explicitly so it's clear what I mean. For optical transitions, man, this is always a good transition. If I'm talking about microwaves or maybe an RF, maybe I start worrying about it. Okay, so what am I going to do? Well, what I'm going to do is say there are fast terms and slow terms. To the degree to which these frequencies are tiny compared to these frequencies, this is a fast oscillation, this is a slow oscillation. So I want to sort of separate the timescales. That's one way you can formally solve this ODE. There's the method of averages, method of multiple timescales. These are known methods in the solutions to ordinary differential equations. So we're going to take away some of the fast oscillation. We're going to say, I'm going to define a new probability amplitude. I'll call it C tilde because tilde is always our favorite thing to do when we want to define a new variable. by factoring out, well, let me do it this way. I'll say CE Why do I define it that way? Let's say that there was no driving. If there were no driving, we would say CE, well, I'm sorry, I should just be, there's no G there. Without the driving, this thing would oscillate like e to the minus I omega t. Okay? So I want to pull out something that oscillates that fast, but I'm going to pull out the term that goes like the driving. Because that's going to allow me to solve these expressions exactly in the right approximation. So this is a slowly varying amplitude. I've factored out a good fraction of the highly fast oscillating term here. Now the ground state didn't have that term, so the ground state tilde is the same as it without the tilde. I just want to define tilde variables. The ground state is the same. So let's plug that in. So far I haven't made an approximation, I've just defined a new variable. So, by the way, this transformation is known in the jargon as, for reasons that are not completely obvious right now, going to the rotating frame. Why? Because I can, well, I'll explain why. Okay, hang on, I have to explain some other things. But let me leave it at that for the moment. Okay, so let's plug that in, and what do we get? So d by dt cg tilde is the same thing as this, which is equal to I omega cosine omega t times CE, which is e to the I omega L CE tilde. No minus. Okay? And d by dt the probability amplitude for the excited state in the rotating frame is equal to the time derivative of e to the plus I omega t times the original amplitude, which is equal to I omega L C tilde plus e to the I omega L t. All right. So now let's plug that back in over there. This then is equal to minus I omega Eg C E tilde plus I omega cosine omega LT e to the I omega LT CG, which is the same thing as CG tilde. So putting that together, I get I times omega Eg, or minus I, no, sorry, I omega L minus E tilde plus I omega cos omega LT e to the I omega LT C E tilde. So, this is now delta. The whole point of going to the rotating frame was to try to get rid of this fast oscillation. We've come down now to a slow oscillation because by assumption, delta is small. We're near resonance, very close to resonance. Delta is near to 0. It's a very small fraction of omega. But we still have to deal with these terms. They're of the same form. This, that we unsuck the half and end up with e to the 2I omega LT plus 1. And then here we unsuck the half again and get a half e to the 2I omega LT plus 1. Okay, so now what we have separated out is everything that's slow. All the time, we have a set of differential equations with terms that are, all of the coefficients are small, and in addition, we have a term which is so let me just write it out. C. Oh, I'm sorry, this was the same thing. It's really this guy that I've got to do, but it's the same thing. Let's just write it over here, excuse me. 1/2 1 plus e to the minus 2I omega t. So that becomes C tilde plus I omega over 2 e to the minus 2I omega LT tilde. And the excited state is e to the I delta. Okay, so far, what have we done? We've made the two-level approximation, and we've gone to the rotating frame. We've rewritten the differential equation in the rotating frame. The reason we did that is that all of this stuff is slowly varying with time-independent coefficients. These terms are rapidly oscillating coefficients. They oscillate very, very rapidly. One can solve such differential equations approximately through what's known as the method of averaging. If the oscillation time scale is way, way faster than the time scale over which these amplitudes change, then to lowest order, we can just time average this over a period. And these terms vanish. So, when you have an ODE with time-dependent coefficients, if all of the coefficients are small, but some of the coefficients are time-dependent, and those time-dependent coefficients change much, much, much more rapidly than these coefficients, those terms are negligible. They're anti-resonant terms. these terms contribute to resonance, these terms don't. And that's what's known as the rotating wave approximation. That's RWA. One can look at corrections to the RWA. That's what I was alluding to in relation to Aaron's question earlier. If you go through and try to formally derive a perturbation series solution to these ODEs using the method of averaging, finding corrections to this neglection, then you find there are shifts in this resonance frequency, known as the Bloch-Seibert shift. But that's something that never comes up in the context of optical resonance because these Rabi frequencies are always tiny compared to the actual optical frequency. If we're talking about microwaves or RF, maybe I have to worry about it. Okay, so in the rotating wave approximation, which is equivalent to the near resonance approximation, because it was the approximation that delta was small compared to frequency. We have simple coupled ODE. Which we can solve exactly. Let's look at the simple case to start. Let's say I was exactly on resonance. If I'm exactly on resonance, then delta is 0. I have these two coupled ODEs, which are easily solved because I can just simply take the second derivative and substitute one equation into the other in a very simple way. So if I do this, what I find is the second derivative of the ground state amplitude in the rotating frame is equal to I omega 2 times the first derivative of this. Plugging that in gives me a minus I squared minus omega squared over 4. And the same equation for the excited state. Right? So those equations can be simply solved. What's our solution? That's a harmonic oscillator differential equation. If there's one differential equation we know how to solve, it's that one. So that tells me that the ground state amplitude as a function of time is the initial amplitude times cosine omega t over 2 plus I2 over omega, the derivative at the initial time, times sine. No, where did I come from? I is not there. That's the solution to that equation. Depends on the two initial conditions, the initial amplitude, and the initial derivative of the amplitude, right? And this is equal to, I came in there, CG at 0 is equal is equal to, the derivative of it is equal to I times omega over 2 the excited state, so this is I, the excited state amplitude at time t equals 0. And similarly, the excited state amplitude is the excited times cosine t over 2, and the same kind of thing. Same substitution of the time derivative at the initial time. Gives me this. So, for example, suppose at t equals 0, the state of the system is the ground state. Then the excited state at a later time, where its amplitude is I and the ground state is cosine. So what we see here is that as a function of time, the probability to be in the excited state, which is the square of the amplitude, which is the same as the square of the amplitude in the rotating frame, because the amplitude of the rotating frame is just a phase times the amplitude in the lab frame. And this is equal to sine squared omega t over 2, or 1 plus cosine, or 1 minus cosine omega t over 2. So, what we see, the solution exactly on resonance, is that we start in the ground state, we go up to the excited state at a time pi later, and then we come back down to the ground state, because the probability to be in the ground state as a function of time is cosine squared of omega t, which is 1 plus cosine So the solution exactly on resonance involves the probability amplitude, and thus the probability to be in the excited state and the ground state to oscillate. And that probability oscillates at the Rabi frequency. Hence the name Rabi oscillations, also known as Rabi flopping. And they're not rabbis, they're Rabis. Although I'm sure he comes from a Jewish family, probably. But they just spelled it wrong. So if I were to look at in this particular case, with the state initially in the ground state, if I calculate that, and at a time pi over omega, I go up to the excited state, and 2 pi over omega, I'm back to the ground state, etc., etc. This is known as Rabi flopping, or Rabi oscillations. Now, one of the ways in which we think about this, that is, makes our interpretation, gives us a picture that's quite useful to think about, is that if I have a for a two-level atom, I can make it a mapping. This is isomorphic to spin 1/2. Meaning I can just make an association. I can think about my two-level atom as a pseudo-spin. It has nothing to do with the spin of the electron. It's just saying there are two levels. And I can think about one of those levels as spin down and the other level as spin up. In which case, the operators that take me from ground to the excited can be thought of as an effective raising operator, sigma plus, and the operator which takes me from the ground, the excited to the ground, is an effective lowering operator, sigma minus, bless you. Remember that sigma x is equal to sigma plus plus sigma minus. Moreover, the projector onto the excited state here is equal to, can be thought of as 1 plus sigma z over 2. And the projector onto the ground state is the identity minus sigma z over 2, where sigma z is diagonal in this basis. So again, these Pauli operators have nothing to do with the spin of the electron. This is just a mapping of the operators associated with the two-dimensional Hilbert space onto the operators that we're familiar with for spin 1/2. So if we do that, we see the following. What was our Hamiltonian? Well, in the rotating wave approximation, we had the following ODE. Sorry. This is the differential equation that we had written down. So the effective Hamiltonian in the rotating wave, in the rotating frame, in the rotating wave approximation is what? Well, it's minus h bar omega times up minus h bar omega. Hold on, let me start it out this way. This is what we had. Which, using this mapping that we've just written down, so our Hamiltonian restricted to the two levels for the two-level atom, when driven near resonance, the dynamics is expressible as an effective Hamiltonian acting on the pseudospin. What does that mean? Well, what does a Hamiltonian do on a spin? The only thing that can happen to a spin 1/2 particle is it can rotate. There's nothing else that can happen to it coherently. I mean, of course, incoherently we can think about it flipping from spin up to spin down, but coherently, the only thing that can happen to it is the direction of the spin can change. And that direction changing is generated by this Hamiltonian. Let's look at the case of resonance. On resonance, delta is 0. When delta is 0, now this, of course, is the identity. The identity doesn't do anything to the dynamics. It does the same thing to both levels, so we can neglect that. The identity doesn't affect dynamics. So on resonance, my Hamiltonian in the rotating frame, in the rotating wave approximation, is given by this. Well, in this case, because we've made the rotating wave approximation, my time evolution operator in the rotating frame is trivial to write down. I can just exponentiate it. We couldn't exponentiate it before because the Hamiltonian was time dependent. And generally you can't just exponentiate a time dependent Hamiltonian. But because we've done the rotating wave approximation, we can just rotate this, and this is then equal to e to the I omega t over 2 sigma x. But you recognize that, right? This is nothing else than a rotation operator. A rotation of the pseudospin. Remember, angular momentum is the generator of rotations. And of course, for spin 1/2, we can write this out exactly. This is cosine omega t plus I sine omega t over 2. This is not get any matrix plus sigma x. You can always express your SU2 matrices that way. So this gives us another way of seeing the Rabi solution. If I say at time t equals 0, the state is the ground state, then the time, this is in the rotating frame, the state is the time evolution operator acting on this, which is equal to cosine omega t over 2 times the ground state plus I sine omega t over 2 sigma x acting on that. Remember, this is spin down. Sigma x acting on spin down is spin up, which is the excited state, right? Which is exactly what we had before. The probability amplitude of the ground state is here. The probability amplitude of the excited state is here. So we think about this evolution in an abstract way. We think about it as the dynamics of a two-level atom equal motion of a pseudospin. If we have a spin 1/2 particle, we can think about it as being defined by a sphere, where this is spin up, this is spin down, this is, say, along the z direction, this is spin up along x, which is the linear combination of spin up and spin down along z, and this is spin down along x, and this is spin up. Oh, well, I guess the way I've drawn it, this has got to be spin down along y, and this is spin up along y, because x cross y has to be z. We make the analogy now and think about this sphere. This sphere is known as the Bloch sphere. Because Bloch was talking about magnetic spins, and we're thinking about the dynamics of magnetic spins. Where now, I make the analogy, it's a one-to-one mapping. It's an isomorphism. This is the excited state, this is the ground state. This is the state excited plus ground over root 2. This is the state excited minus ground over root 2. This is the state excited minus I ground over root 2. This is the state excited plus I ground over root 2. And so, what are Rabi oscillations? Rabi oscillations can be thought of as the rotation of the pseudospin on the Bloch sphere. If I have a rotation operator like this, that means I'm rotating around the minus x-axis with a frequency omega over 2. So here's my torque vector. I then rotate around this equator. Well, it's the whatever, North Pole, South Pole, great circle. Oscillating between ground, excited, back to ground, back excited. I think about that oscillation as the precession of a pseudospin on the Bloch sphere. And according to the picture I just erased of the oscillations, after a time pi, when the time here is such that this is pi, I come up here. At 2 pi, I'm back down here. Hence, if I apply this for a time pi, I invert the atom from the excited to the ground. That's called a pi pulse. And if I did it for 2 pi, I'd make a 2 pi pulse. But notice, intermediately, if I apply it for pi over 2, for example, I'm here. I am in a coherent superposition of ground and excited. So this is one of the important points, and we'll stop here, is that when I have well-defined energy levels that are discrete, that are not smeared out by some density of states, and when I have a very well-stabilized, very narrow band laser frequency, then intermediately, I don't think about going from a quantum jump from excited to ground, but I think about a coherent superposition. I am creating intermediately a coherent superposition of ground and excited states. And if I apply this laser field for exactly such that the Rabi frequency, which depends on the dipole matrix element, and depends on the intensity of the field, if I apply that such that that time omega t is equal to pi over 2, this system would become an equal superposition of ground and excited with a particular phase between them. We'll pick that up again next time. Modes, so that we don't really have purely monochromatic radiation. For example, we have quasi-monochromatic radiation with some spectral density of the power at a given frequency. And from this, we saw last time, we looked at the absorption rate in the kind, if we had, for example, absorption of black body radiation, specified by a energy density per unit frequency interval, then the absorption rate was written as something we typically call the Einstein B coefficient times the spectral energy density. And B here was equal to 4 pi over 3, the square of the dipole matrix element between the ground state and the excited state, h bar squared. That's the Einstein B coefficient, I believe. Right? I think that's right. Okay. And then we also talked about spontaneous emission. Well, and of course, this would also be equal to the rate of absorption from the ground state to the excited state given by this. That's what we call, that's our absorption rate. But in addition, if we had started in the excited state, then we would induce transitions to the ground state by the same rate. And this is what we call stimulated emission. It's exactly the same rate. Relations are not with well-defined phases. Moreover, when we're talking about spontaneous emission, we're talking about vacuum fluctuations, which are also highly incoherent. So Fermi's golden rule, if you go back, I don't know if you remember, or if you've done this in your quantum mechanics course, the derivation of Fermi's golden rule, you feel like you have to stand on your one foot and, you know, be grasshopper and make sure you don't move. And you're talking about perturbations, which are supposed to be short-time evolution, but then you take the limit as t goes to infinity, and you say this thing is really for the long-time limit, but that's okay because really, I don't know why. Well, it's all buried in the fact that the situation for which Fermi's golden rule holds are the situations for which we have this distribution, this density, this spectral density of final states or spectral density of driven modes. But that's not all there is in the world. For example, if I'm thinking about say I have an atomic clock, in cesium. Okay, here's my 6-1 S1/2 ground state. Here's my n equals 0. And I put on a microwave radiation, electromagnetic wave, which is driving this transition. If I somehow started my atoms here. I can calculate, if I like, I can use Fermi's golden rule to try to calculate the rate of absorption. In this case, it will be a magnetic dipole transition between those different levels. But that's a little bit narrower of a view, because of course we know that indeed, according to quantum mechanics, evolution is generated by a unitary time evolution operator, in which probability amplitude continuously evolves according to the time-dependent Schrödinger equation. So really what we want to talk about today is life beyond Fermi's golden rule. You know, in many subdisciplines of physics, as a biased quantum optician here, you know, you talk to your typical condensed matter physicist and it's all about correlation functions and what's the ground state. It's all statics. Dynamics is, you know, you just throw in Fermi's golden rule. It just tells you how things, how you absorb and emit your matter if you're not in equilibrium. And that's a very useful picture to have when we're talking about incoherent processes. And we're going to talk a little bit about the difference between coherence and incoherence in the next few lectures. But the point here is that these two particular examples are examples of incoherent processes. I'm talking about not a well-defined electromagnetic oscillator that's oscillating with a well-defined frequency, really. What I'm talking about is chaotic light that's coming from this light bulb or from a thermal source like the sun. If I were to look at the electric field as a function of time, it is not oscillating with a well-defined frequency, but in fact is jumping all over the place because there's a very chaotic process by which all the collisions of the electrons being driven in this gas of neon tubes or in the sun, which causes the emission, the radiation to be constantly interrupted, all the oscillations. However, in addition, we saw that there is spontaneous emission, in which we interpreted as be thought of as stimulated emission by the vacuum. And so the spontaneous emission rate is the B coefficient times the vacuum energy density, which we call the Einstein A coefficient, which is also the natural line width of the excited state, and the Einstein A coefficient, or the spontaneous emission rate, that's 1 over the lifetime, is equal to 4/3 the dipole matrix element squared times omega cubed. Okay? So in addition to the stimulated emission, there is also spontaneous emission at the rate gamma, given by, which means that there is, even in the absence of any electromagnetic radiation, the excited states are generally not stable. They're not true eigenstates of the total system because of the interaction with the vacuum fluctuations. All right? Okay. So, well, this is a particular picture that we have of absorption emission in which we think about rate processes, in which we think about there are energy levels of my atom or molecule or what have you, and the effect of the perturbation by the magnetic field is to cause population to jump of electromagnetic radiation. And so what we're looking at is the situation where we are near resonance with some transition in our atom being driven by quasi-monochromatic light. So we can think about this as a plane wave, although it's not important that's a plane wave. It could be a standing wave. Just the fact is that we have some fairly well-defined frequency. And if we are in the electric dipole approximation, then our interaction Hamiltonian is the interaction of the electric field associated with the electromagnetic wave and the electric dipole operator of the atom. And if we express our general plane wave in terms of the real part of this complex amplitude with a polarization vector and a propagating wave, then our interaction Hamiltonian breaks up into two terms we generally call the positive and negative frequency components. And when you go through the usual derivation based on time-dependent perturbation theory, then you get from Fermi's golden rule the transition rate between some initial state and some final state, which depends on the matrix element of either the positive or negative frequency component, depending upon whether the initial and final state are greater, if the final state is greater in energy by h bar omega, or less than in energy by h bar omega, corresponding to absorption or emission. And this expression only really makes sense when we are integrating over some spectral distribution of either the density of states and or some density of